Hello everyone, welcome to the Blue Economy CRC webinar series for 2026. I'm Professor Irene Pennesis and I'm the Research Director in the Blue Economy CRC, and I'll be helping facilitate this session today. I'd like to just begin by acknowledging the Palawa and the Pakana people, who are the traditional owners and custodians of the land in which I am broadcasting to you from today, which is in Launceston. I pay my respects to the elders past and present and emerging, and I also extend that respect to all First Nations people joining this virtual meeting from other lands and waters across Australia. The Blue Economy CRC is an organisation that's got a 10-year life. It's assembled 46 past and present industry, government and research partners from 10 countries with deep knowledge in expertise in aquaculture and marine renewable energy, maritime engineering, environmental assessments and policy and regulation. We currently work with 41 active participants from 9 countries, and we're supported by a very big network of strategic partners and third parties on the projects that we're involved in. Through our targeted and industry-focused research and training, the Blue Economy CRC drives innovative, commercially viable, sustainable offshore developments and new capabilities that will significantly boost the renewable energy output, the seafood production and job creation. We are transforming how Australia's oceans industries operate and grow through our vision, our purpose and our values. I'm pretty excited to bring today's webinar to highlight to you today 4 of the presentations held from the Blue Economy Symposium, which was part of the OMAE 2026 conference in Tokyo in Japan. For over 4 decades, the OMAE conference has been a premier annual event to showcase some of the leading edge innovations and technology advancements in offshore engineering. And owing to that success, we established the Symposium on the Blue Economy, which has now become a permanent fixture in the OMAE conference. And we're very lucky that it has the opportunity for us to cover a lot of the context of the blue economy with a focus a lot on aquaculture and renewable energy applications, but also in the context of emerging technologies as well. So I've been very fortunate to have presented in the Blue Economy Symposium now for the last 4 years. And today, actually, I'm going to bring to you some speakers, 4 presentations from those sessions, including both from Blue Economy participants and other collaborators and organisations internationally who are working in this space. A Q&A session will follow after the presentations, which I will facilitate in conjunction with Dr. Yunil Chu from the University of Queensland. But at any time, if you've got questions, don't hesitate to put them in the Q&A box at the bottom of your screen. And you can, of course, upvote any questions you wish to be answered so that the popular votes get prioritised first. And our presenters, when they get a chance, will also respond to the questions in the list as well while the webinar is live. So without any other delays, I want to start by introducing our first presentation, which is on the development of an integrated CFD framework for simulating artificial upwelling and flexible kelp dynamics in offshore environments. This is going to be presented by one of our PhD students in the Blue Economy CRC based at the Australian Maritime College, University of Tasmania, and that's Mr. Ali Matamed Hazard. Thank you, Ali. I welcome you to present your presentation with us. Hopefully, you can share your slides on the screen directly.
Thank you so much, Irene. Okay, just let me share my screen. Okay.
And we can see them. Thank you very much, Ali.
Yeah. Thank you for confirming. Hello, everyone. Thank you for joining us today. My name is Ali Motamedinejad. I'm a 4th-year PhD candidate at the Australian Maritime College, University of Tasmania. My research is part of the Blue Economy CRC offshore seaweed aquaculture projects. And today I'll be sharing some of the numerical modeling results that I recently presented at the OMAE conference in Tokyo. I'll begin with some background on kelp cultivation and the motivation for artificial leveling. Then I'll give you an overview on the numerical framework and the model validation. Next, I'll present the preliminary results. And finally, I'll conclude with the key findings and future work. Giant kelps belong to the brown macroalgae seaweed category. Kelp forests are among the most productive ecosystems on Earth. They provide habitat and food for many marine species, capture carbon, oxygenate the surrounding water, and naturally recycle inorganic nutrients. The map on the right shows the global distribution of the kelp forest and their dominant genera. Today, kelp is already used across a wide range of industries. As shown here, it can be used for human consumption, for biofuels, fertilizers, bioplastics, animal feed, and for extracting valuable compounds such as alginate. This wide range of applications highlight the growing economic and environmental importance of kelp cultivation. Currently, most seaweed aquacultures take place in the nearshore waters where available space is limited and often subject to competing uses. So to meet the growing demand for sustainable seaweed production, expanding cultivation into offshore environments is becoming increasingly important. However, offshore surface waters are typically warm and nutrient poor, which creates a major challenge for larger scale kelp cultivation. This challenge is particularly important here in Tasmania. The waters around Tasmania are warming rapidly. As shown here in these maps, sea surface temperatures have increased significantly over the past 2 decades. Another challenge is the nutrient availability. Results from the CSIRO Storm Bay project show that during summer, nutrient concentrations in surface waters are very low. Most of the available nutrients are found at the depths of like 100 meters and below, where water is also cooler. To address this challenge, artificial upwelling has emerged as a promising solution. The idea is to bring cool, nutrient-rich deep water up to the surface to support the kelp growth. This can be achieved by different technologies, including wave-driven, electrical, or airlift pumping systems. Although this is a growing research area, significant gaps still remain. Existing studies have mainly focused on either seaweed hydrodynamics or artificial plume transport separately. But this study addresses the gap by developing a coupled CFD-DEM framework to investigate their interaction under offshore conditions. These governing equations describe the three key components of the integrated modeling framework. They represent the flow field, nutrient plume transport, and the flexible kelp model. And the passive scalar and the DM models will be briefly introduced in the following slides. Nutrient plume is modeled using a passive scalar, which is similar to tracer dye, which is used in laboratory experiments. It tracks the transport and dilution of the plume through advection and diffusion. And to capture the buoyancy effects, the scalar field is coupled with the momentum equation using this user-defined field function. The flexible kelp is also modeled using the discrete element method, or DEM. The blade is represented by a series of connected elements that deform in response to the surrounding flow. And through two-way coupling, the flow influences the blade motion, while the blade motion also affects the surrounding flow field. This figure shows the numerical setup used in this study. The computational domain consists of a 1 to 25 numerical wave tank, a 5-line array kelp platform, and a single artificial upwelling outlet. These components are fully coupled within the integrated CFD framework. The computational domain was also discretized using a structured trimmed cell mesh model, and refinement zones were applied around the regions of interest, resulting in a final mesh of around 5 million cells. These tables summarize the key modeling parameters used in this study, including the offshore hydrodynamic conditions, the artificial upwelling system specifications, and the physical properties of the flexible kelp model. So the first validation phase was focused on the artificial upwelling plume. The CFD results were compared with the experimental data published by Contini and Robbins 2001, and as shown in the plot, the predicted plume centerline elevations agree very well with the measurements, with an average error of less than 3%. And the second phase of the validation was focused on the flexible kelp models, and the predicted blade reconfiguration was compared with the experimental measurements reported by Luhar and Neff in 2011. And as shown in the plot, the effective blade length agrees well with the experiment, with an average relative error of less than 5%. Okay, so first we look at the qualitative plume evolution under current only, wave only, and the combined wave current forcing. The top view row shows the cases without kelp, while the bottom row includes the flexible kelp canopy. Okay, the videos clearly highlight the different plume behaviors under each hydrodynamic condition. Under current-only condition, plot A and B, the plume remains relatively compact and with limited vertical and lateral spreading. The presence of the kelp introduces a smaller scale turbulences, resulting in a slightly greater mixing. Under wave-only condition, the wave orbital motion generates a strong plume oscillations, increasing both vertical and lateral dispersion, and the kelp presence also contributes to keeping the plume within the farm region. And finally, under the combined forcing condition, the plume becomes more deformed as wave-induced oscillations interact with the current, while the kelp canopy promotes greater plume retention within the upper farm region. Okay, next we examine the lateral plume dispersion within the kelp farm, again under the current only, on wave only, and also under the combined condition. And again, the top row shows the cases without kelp, and the bottom row shows the simulations with the kelp canopy presence. And these videos are from the top view. Okay, from this plot, we can clearly see that the presence of the kelp canopy consistently broadens the plume by enhancing the cross-stream mixing. Under current-only condition, the plume expands gradually downstream as the kelp redistributes the kelp laterally. And under wave condition, the wave oscillations accelerate the lateral spreading, while the flexible kelp further enhances the plume mixing within the farm. And on plot C, as you can see, in wave and current combined condition, the plume reaches its maximum lateral spread before the middle of the farm, indicating more efficient lateral distribution within the canopy region. This figure also shows the percentage of the enhancement in lateral plume spread due to the presence of the kelp. So basically, it's the comparison between with and without kelp conditions. And as you can see, under wave-dominated conditions, the largest enhancement occurs on the upstream section of the farm, while for under current-only condition, the enhancement develops more gradually and reaches to maximum further downstream. Finally, we investigate the plume vertical mixing. And as you can see, again, we got the videos for current only, wave only, and their combination. So these videos are from the side view to better show the vertical mixing uh, within the water column. These plots show the influence of the kelp canopy on vertical mixing. They show that the vertical mixing actually depends strongly on the hydrodynamic condition. As you can see on plot A, under current only condition, the plume gradually deepens as it travels downstream, while the presence of the kelp enhances the vertical entrainment and increases the plume thickness. Under wave-only condition, the wave orbital motion rapidly homogenizes the plume, making the influence of the kelp canopy relatively small beyond the upstream region. And finally, on the combined condition, a similar behavior is observed, with wave motion dominating the vertical mixing and the effect of the kelp mainly limited to the entrance of the form. To conclude, this study developed and validated an integrated CFD-DEM framework for assessing nutrient delivery from artificial upwelling system in offshore kelp farms. The results show that wave orbital motion is the primary mechanism driving vertical mixing, while the flexible kelp canopy enhances the lateral plume dispersion and the plume thickness, particularly under current-dominated conditions. And looking ahead, this framework provides a foundation for investigating different kelp densities and farm configurations, full-scale offshore conditions, multidirectional artificial upwelling systems, and ultimately coupling nutrient transport with kelp growth. Finally, the authors would like to acknowledge the support provided by the Blue Economy CRC as the project sponsor, Next Wave Civid as the industry partner, the University of Tasmania High Performance Computing team for providing the computational resources, and also the Siemens team for their technical support. And thank you everyone for your attention, and I'm happy to take any question. Thank you.
Thank you so much, Ali. That was excellent. I can see that you've sparked some interest in your presentation in the Q&A, so I hope that you'll take a moment to review some of the Q&A, and we obviously can answer some of those questions in the Q&A session at the end of the webinar. So thank you very much, Ali.
Yes, no worries. Thank you.
And I now want to welcome our second speaker, Dr. Hongjung Fang, who's from the Australian Maritime College as well at the University of Tasmania. Good afternoon, Hongjung. Thank you so much for being here. Hongjung is an expert in offshore engineering and hydrogen, and he's one of our research fellows. And actually, he's been doing some work in offshore wind. So I would welcome Hongjung to share his slides. He'll be presenting to us on decarbonising offshore wind operations, a concept design of a hydrogen-powered system for a service-operated vessel, so an SOV. So thank you, Hongjung. I'm very happy to pass it over to you for your interesting presentation.
Thank you, Professor Erin, for your kind introduction. Good afternoon, everyone. So today I'd like to present our research work on a conceptual design of hydrogen power systems for an offshore wind service operation vessel, or SOV, for decarbonizing offshore wind operations. So this paper is co-authored by Associate Professor Peggy Chen from Australian Maritime College, Mr. Andrew Harris from BMT Australia, Dr. Naji Abdulsami from University of Doha for Science and Technology, and Professor Erin Penesis from the Blue Economy CRC. Actually, this work is part of two Blue Economy CRC projects, one on hydrogen-powered vessels, and the other on preconditions for offshore wind development in Australia. And if you are interested in the full report, you can have a read from the Blue Economy CRC website. As we know, Australia is planning large-scale offshore wind developments. One of the most active areas is Gippsland in Victoria. Several offshore wind projects have already been licensed for feasibility. As these projects move forward, there will be increasing demand for SOVs to support operation and maintenance activities. So what is our research motivation for this research? Offshore wind produces clean electricity, but maintaining offshore wind farms still relies on fossil fuel powered vessels. So this is a paradox. We are building renewable energy projects, but supporting them using fossil fuels. So we had a simple question. Can offshore wind operation also become zero emission? To answer this question, we focused on three practical questions. First, can hydrogen replace diesel power? Second, can enough hydrogen be stored on board? And third, which solution makes the most practical sense? To answer these three practical questions, using an existing SOV as the benchmark vessel, we carried out a like-for-like comparison to see the differences between diesel-fueled vessel and hydrogen-fueled vessel. This is our benchmark vessel. She is a modern offshore wind SOV. The vessel is 73 meters long. The vessel can accommodate 60 people. She has a 30-day endurance, and the power system is diesel electric with 4 diesel generators. And its power demand is 5.2 megawatts. And the vessel emits about 17,000 tons of CO2 per year. So this is a big number for the CO2 emission. The first challenge is to replace diesel engines with hydrogen power systems. We evaluated 2 hydrogen technologies. On the left-hand side, as you can see, is the PIME fuel cell system. On the right-hand side is hydrogen internal combustion engine. Both technologies today are available on the market. And the question is whether they can provide sufficient power for this benchmark vessel. The short answer is yes. Both options can provide the required power. However, the PIME fuel cell system is lighter and more efficient than hydrogen internal combustion engines. So from this point forward, we selected the PIME fuel cell system as the preferred option. The next challenge is hydrogen storage on board. It is the real problem because, as we know, hydrogen has a very high energy density by mass, but it has a very, very low energy density by volume. So how do we store enough hydrogen on board? We studied 4 hydrogen storage options: compressed hydrogen, liquid ammonia, and metal hydrate. This figure compares the storage options. On the left is hydrogen content by weight. On the right is energy density by volume. Liquid hydrogen and liquid ammonia provide much higher energy density. But if we compare them with diesel, diesel still has a major advantage in volumetric energy density. So this is why hydrogen storage is the key challenge for vessel. Next, we evaluated actual fuel volume and weight required for the benchmark vessel. Because of storage limitation, we reduced the vessel endurance from 30 days to 14 days. And we had a conversation about 14 days endurance with an offshore wind developer, and 14 days is also acceptable. For 14 days, the total electrical energy demand will be 1,139 megawatt hours. So let's see this bar chart. The dashed line represents the benchmark diesel vessel. And the results show that compressed hydrogen requires extremely large tanks. And metal hedges require excessive weight. So they are not practical for this benchmark vessel. Only two options remain feasible. They are liquid hydrogen and liquid ammonia. Then let's look at the arrangement for the vessel. Diesel system is a baseline for the design. The vessel currently carries about 560 cubic meter of fuel with a weight of about 500 tons, including fuel handling equipment. This is as you can see here, the blue box. This is a freshwater tank. And this slide shows the liquid hydrogen solution. The vessel requires two 500 cubic meter liquid hydrogen tanks. The total storage system weight is about 680 tons, a little bit heavier than diesel. So the vessel's stability will be impacted. We need to do further study about this. And freshwater tank has to be removed. We need to find other spaces for freshwater storage. And the arrangement is technically achievable. And hydrogen is supplied to the fuel cell system through evaporation and the conditioning system. And this is the liquid ammonia. The vessel requires two 330 cubic meter ammonia tanks. And this volume is smaller than the liquid hydrogen. And the freshwater tank can remain here, so we don't need to remove it. And hydrogen is supplied to fuel cell system through ammonia cracking and the purification process. Therefore, liquid ammonia is also feasible. And technical feasibility is only a part of the research. Economics is equally important. So this figure compares annual total cost of ownership for this benchmark vessel. Diesel remains the lowest cost option, and the liquid hydrogen system is most expensive, and the liquid ammonia system performs better than liquid hydrogen. However, both hydrogen solutions are still more costly than diesel today. So our conclusion is hydrogen is technically ready, but economics remains the challenge. And these are the key takeaways from this paper. First, hydrogen powered SOVs are technically feasible. Second, among the storage options evaluated, only liquid hydrogen and liquid ammonia are practical. And third, liquid ammonia currently offers the best balance between feasibility and the cost. And another question remains. You may ask, where is the hydrogen and ammonia from? So I'd like to leave you with the future vision. Actually, liquid ammonia and liquid hydrogen can be produced by offshore wind turbine and the sea waters. So in this way, offshore wind farms could eventually support their own supporting vessels. We made a rough calculation. Only one 15 megawatt wind turbine can support this vessel's bunkering. To conclude my presentation, let's keep one message in mind. Green wind needs green ships. So this is my presentation. Thank you.
Thank you, Dr. Fan. Thank you very much. Very nice conclusion. Something we've got to keep an eye on, in particular when it comes to green hydrogen as well and offshore wind. I appreciate that. I'm sure there'll be plenty of questions in the Q&A which we can address later and during your presentation.
Yep.
So I thank you for that. I'm
Thank you.
going to now invite our next speaker, if I can, which is Associate Professor Xianfeng Guo from South China University of Technology, who's going to talk to us about a brief review on large offshore aquaculture facilities in China. Very interesting presentation. So thank you so much, Xianfeng, for joining us here and presenting with the Blue Economy CRC in the webinar. Please feel free to share your slides on the screen.
Yes, thank you very much for the introduction.
Obviously, we always love hearing your presentations, hearing about the latest activities in offshore aquaculture happening in China. You're definitely on top of all of these. So I invite you, yes, to start. Thank you.
Thank you very much. So hello to everyone. My name is Xiangfeng Guo from South China University of Technology, and I feel a great pleasure to be a part of this webinar. Actually, our team and we all benefit from the webinar, the previous versions. So I feel great that I can be a part of this webinar. So thank you to the BECRC for keeping organizing this event. And this is the agenda for my presentation. I will start by giving you some background related to our offshore aquaculture in China. And then I will present 94 large offshore aquaculture facilities we collected during last year, which were installed the last 10 years in China by 4 categories. It will be followed by analysis on the regional deployment pattern of these 94 facilities. And I will end the presentation by giving you some thoughts on future developments. So the main objective of this presentation is to give you some quick understanding or a broad overview about what is happening or what has happened in China about offshore aquaculture, especially the large facility installed. Okay, so traditionally, when we talk about marine aquaculture, we focus mainly on nearshore aquaculture, where we use gravity cages or fishing rafts to farm fish. But they are facing increasingly challenges like limited space because we have many activities in the nearshore and poor exchange, high risks of disease. So people are seeking for large space and better water exchange in the offshore areas. That's why you can see last 10 years, China is also in this trend. So they have invented a wide range of different facilities and install them in different coastal areas in China to withstand the harsh environments. So we have benefits from offshore areas, but of course we have some challenges like harsh environment, strong waves, and the difficulty to operate to maintain the operation. So today I will quickly review the large facilities we have installed last 10 years for the purpose of fish farming in aquaculture in offshore areas. So here is a timeline showing that during last 10 years we have indeed a boom of the offshore aquaculture facilities in China. Here in the timeline, I give you some key milestones. For example, in 2017, we launched the first aquaculture vessel, so which marked the beginning of industrialization of our market in offshore aquaculture. Since then, a series of policies from national and provincial levels are released. So these policies have supported a lot the development by combining industry, academia together, by investing money. So under the support of these policies, we have installed around 100 large facilities during the 10 years. So I will review them in the next slides. By 2024 here, we found some figures, some numbers, so you can get a quick, a big picture about what we have reached so far. So when we talk about deep sea aquaculture in China, the total farming volume now is 65 million cubic meters, with annual production is about 500,000 tons for deep sea aquaculture. So here I want to highlight that in China, we may have a different definition of deep sea farming because our continental shelves is relatively large. So the water depth is increasing gradually, not dropped rapidly. So that's why we define that if you farm in a water have a depth higher than 20 meters, or you are 10 kilometers far from offshore shoreline, you are doing deep sea farming in China. So all the figures here correspond to the deep sea farming in our country. Okay, so in this study, we focused on the 10 years and we collected the large facilities installed in the 10 years. Actually, we found information of 94 facilities. Theoretically, we should have something around 100, but we finally found only information of this 94, including 84 truss-based structures, floating or fixed, and then 10 aquaculture vessels in together, 94. I also want to highlight that in our study, we didn't consider the gravity cages fishing rafts for the review. We just focus on the truss structures and aquaculture vessels because they have more advanced technologies and they have more engineering challenges. Okay, so in the next few slides, I will present the 94 facilities we collected by 4 categories. So we classify them into 4 categories: floating ones, fixed ones, aquaculture vessel, and integrated facilities. Here I give you also one examples for every category, so you could have a quick look at what it looks like. Well, the classification approach we adopt here is not perfect because you can see aquaculture vessel is also floating. Integrated facilities can be floating or fixed, but we still adopt this classification approach because it is quite widely used in China. And the last 2 categories indeed have their distinctive features, which can justify them as a separate category, which I will present later. Okay, so the first category, floating facilities. Well, further we can classify them into fully submersible or semi-submersible floating platforms. Compared to fixed platforms, obviously we have a higher adaptability to waves, and they are more suitable for deep water deployment by using mooring system. And here in China, I want to highlight that such category is usually deployed in a cluster way, combining a number of gravity cages as shown by this figure. So by doing this way, we formed 1+N marine ranching model. So 1 here represents the large facility, the floating facility here, which is not only a farming unit, but also can provide some central station functions. And then in the venicity of this facility, there are a number of gravity cages. So together we have so-called 1+N marine ranching model. And the second category is the fixed facilities. So they will be connected to the seabed by piles or by other foundation types. And they can provide, because the piles, they can provide a relatively higher stability with small motion. And because the piles going to the seabed, they allow us to farm some shallow or bottom favored species. And again, in China, they have a specific feature Well, actually, because they have a small motion, high stability, that allowed us to explore multi-function in a single platform. For example, this one, from the perspective of owner of offshore wind farm, it's easier for them to accept a fixed facility for fish farming installed in their fish farm compared to a floating one. So they are integrated in the fish farm area. And another example is Genghai number 1. They actually combine fish farming in this area with a luxury hotel. So allow us not for aquaculture, but for tourism as well. Then the third category, mobile facilities, aquaculture vessel. So obviously, the one biggest advantage of such category is that they can operate in any sea area, theoretically. For example, they can farm fish in northern part of China in summer, and then in winter they can travel 1,000 kilometers to southern part for the purpose of finding a suitable water temperature, for example, or to avoid some strong storms or typhoons here. So this is biggest advantages, and some vessels are also equipped with enclosed cages to have fully controlled conditions, have better quality of water. And on the other hand, for now, the biggest issue is that they are quite expensive. The high cost is obviously is one barrier of this category. According to my knowledge, the unit price of such category is like 4 to 6 times higher than the one of fixed or floating facilities I presented before. Then the last category, integrated facilities. And before we have seen co-location integration, which we built a facility for fish farming in wind farm area. Here, I focus on another type of integration. We call it co-structured integration. So here are 2 examples. We use bottom fixed, actually jacket offshore wind turbine to farm fish inside. And the bottom one, we use floating structure, a floating wind turbine to farm fish inside the floating platform. Well, I must say that such type of category is still in the pilot and demonstration stage because as you can see or read from papers, they have still many challenges and issues. For example, the design complexity, the operation, and also the influence of wind turbine on the fish welfare. So still, I think there are challenges remaining to be resolved. Okay, let's move on to the third part of my presentation, where I will analyze quickly the regional deployment of facilities, aquaculture facilities in different provinces along the coastal line in China. So from the map in the left side, you can clearly identify 3 major players, 3 major provinces in China for offshore aquaculture. Shandong province in the northern part, and Fujian, Guangdong province in the southern part of China. Then, moreover, from the bar chart, you can also identify the differences of facilities they use in their sea areas. So in northern part, in Shandong province, the fixed bottom fixed facilities are dominant. And then in the southern part of China, they mainly use the floating facilities with some integration facilities also explored. Well, such a difference is mainly because they have quite different water conditions, mid-ocean conditions. For example, in southern part of China, we have relatively stronger currents, and the facilities are exposed to typhoon or storms with more frequently. So in this way, they prefer to have a floating structure with mooring system so that they can adapt more easily, more stably to the strong or harsh environment. And then in this slide, I will show the different species we farm in different provinces. First, look at this figure. From south to north, I show you 4 provinces. And in the x-axis, I present some major species we farm. So again, we can find a pattern from southern to northern part in China. Different provinces have different species, like in Shandong, they have cool water, so they can farm salmon, which is theoretically not possible in southern China. In southern China, they farm the coracle, like yellow coracle or brown coracle. Sometimes they also farm cobia. So this shows the diversity of species we farm in China, as well as different species favored in different province. Okay, the last part is about some thoughts from our team on the future development, not only in China, but also for over the world. Actually, we read some papers. We found actually 2 directions. Here I show you 2 boxes. One box, the top one, shows the emerging trends where people already know their importance. They are working on it. For example, integrate it with wind turbine, with WEC, etc., to use the renewable energy. Cluster deployment, like 1+N model I presented before. Digitalization for intelligent operation, and then advanced cage engineering, as well as underwater robots, especially for biofluid issue. And then the bottom box shows you some challenges or priorities we identified by summarizing the information, by comparing different studies that we believe they also need great attention. But till now, we have not invested enough money or time or efforts into these aspects. For example, the biological performance of fish welfare. So we can design very well structures, but till now, we don't know very well how fish perform during the service life. And then the industry chain integration, how we can systematically optimize the chain from fish juvenile training and then to the production end to end, and make the process optimal in terms of economy and efficiency. Then we have also some other issues like economic. Well, in China, as you can see, many facilities installed, but they have done this with some support from government. So we don't know in few years, without this financial support, how we can do this with this installation. So economic optimization will be definitely a research direction. I will not go into details for every aspects, but anyway, here I show you 2 boxes with 2 directions, 2 aspects. Okay, thank you very much for your attention, and thank you also to my collaborators. Actually, this is a study from collaboration between us in China and UQ from Australia. Thank you. I will happy to take any questions.
Thank you very much. I appreciate your presentation. And I will invite you to answer some questions afterwards as well. So please stay for our next speaker as well. So thank you, Xiang Feng. I'm going to invite our next speaker. So thank you very much, Reza Abbasi, for joining us today. Reza is a PhD candidate in the Blue Economy CRC. He's based at the University of Queensland, and he's going to be joining us today to give us a presentation about the power absorption of axisymmetric and symmetric float shapes in regular and irregular waves, and it's an experimental investigation with a PTO, so it's related to wave energy. So thank you, Reza.
Thank you, Irene, for introduction and arranging this webinar today. Thank you, everyone. Do you have my screen?
We absolutely can see your screen. Thanks.
Thank you so much. Good afternoon, everyone. I'm Reza Abbasi, a final year PhD candidate at the University of Queensland. Today, I'll present our work on wave energy converters that present recently in Tokyo, focusing on influence of float shape on power absorption. This project is supported by Blue Economy CRC. Thank you for joining. So the presentation today will cover introduction, literature review, methodology, and at the end of the day is question and answer. Before introducing my research, I'd like to briefly explain the motivation behind it. As we know, the global demand for energy continues to increase, while at the same time we are trying to reduce our dependence on fossil fuels and lower greenhouse gas emission. So this creates a strong need for reliable and sustainable renewable energy sources. Among these, the available renewable energy resources, ocean wave energy has a very high demand and density, and it's available in many coastal regions, especially in Australia. Many different wave energy converters concepts has been proposed over the years. For example, the devices show at top right, like a point absorber, and down is the wave star, and the other one is M4. The image at the bottom shows an experimental model of M4 and IMC. In this work, we investigate how different flow geometries influence the hydrodynamic behavior of wave energy converters and power absorption of multi-body wave energy converter. So there are many studies in the literature from early development of wave energy converters so far to present today, but I have brought just some of them from recent years, investigating the effect of flow geometries on device performance. Researchers have examined various float shapes and different degrees of freedom, showing that geometry strongly influence hydrodynamic behavior and power absorption. More recent studies have also explored asymmetric and optimized geometries to further improve efficiency. This finding actually shows that the importance of the float design. However, experimental studies on different float geometries in multi-body system with a realistic power takeoff system or PTO remain limits. So one of the energy converters is the M4, as I presented. It's a multi-body wave energy converter consisting of bow float, mid float, and aft float. And the aft float connected by rigid beams. The left side is the deployed. This is a picture of the deployed one, and is the scale model on the right side at AMC. And energy is extracted from the relative rotation motion between the bodies through a rotational power takeoff system, as you can see from top side of that. And for this research, only the aft part was considered as an individual wave energy converter. So based on literature review, we identify several research gaps. First of all, although the flow geometry is known to strongly influence the hydrodynamic behavior and energy capture of wave energy converters, the mechanism of them are not yet fully understood. And the second is most research is conducted numerically with no experimental test and power takeoff system. And also certain float shapes are designed for specific modes of motion, like wave star device for HEAV. So this is the flow chart of present the overall methodology and summarize all the steps we have done in this work. Starting from the design stage, we first check whether the natural frequency matched the target value. The target value was the natural frequency of the hemisphere bottom. HB here is the hemisphere bottom, which is the the reference float from the M4 device. If the natural frequency was correct, we proceed to the next step. The next step include both numerical and experimental parts. The left side shown in blue represent the experimental work, while the right side shown in green represent the numerical model. In the numerical model, we first obtain the hydrodynamic coefficients such as radiation damping, added mass, and other coefficients, and then perform the time domain analysis. And then when we got all the results, we started data processing and compared them with the experimental model, and then find the efficiency of the model. So before introducing the different flow geometries, I'd like to explain the motivation behind using asymmetric shapes. The motion of wave energy converters is governed by the equation shown at the top left, which coming from the Newton's second law, and where the response depends on the excitation force, hydrodynamic coefficients, like A is the added mass, B is the radiation damping, BPTO is the damping coming from the power takeoff system, and like hydrodynamic stiffness and other external forces. Since the flow geometry directly affect these hydrodynamic coefficients, changing the flow shape can significantly influence the device motion and power absorption. So one concept that is particularly important in the radiation directionality factor shown here from the literature, this factor compared the wave energy radiated in incident wave direction with the energy radiated in the opposite direction. For symmetric float, the radiated wave energy is essentially the same in both directions, so giving a directionality factor of about 0.5. These results are theoretically. So in contrast, asymmetric float can radiate more energy in one direction than the other. Therefore, our hypothesis is that carefully design asymmetric flow geometries that can improve the hydrodynamic performance and power absorption. So this slide summarizes the methodology used in this study. We started with HB float, as I mentioned, is hemisphere bottom as a reference geometry, and designed two additional floats on right side, as you can see. One of them is CH, cone hemisphere, and the other one is HW. And the three models were then manufactured and tested experimentally in parallel with numerical analysis to calculate the hydrodynamic coefficient and validate our numerical results. So for the experimental arrangement, as you can see here, is the sketch of flume and at the location of the setup inside the flume. The flume was equipped with several items, as you can see here, including wave gauges placed before and after the setup, sensors, and a wave absorber at the end of the flume to minimize wave reflection. Also, in this picture, you can see the actual float installed at the test location. So the first step of our experiment was selecting an appropriate damping for the system. So we selected linear damper in which both chambers were connected through a tube and linked to a needle valve, which allowed use to control the airflow between the chamber, and we could adjust the damping level. So as you can see from the sketch, we connected this damper and tested in using MTS device or material testing system in the structural lab at UQ, which applied a displacement and force at a specific velocity to the damper. And using a linear damper, we measured the output of, linear load cell. We measure the output of the device. So as shown in the sketch, the damper was connected to MTS device and control the motion at a specific velocity. And as you can see here, The MTS setup consists of upper fixture and a lower fixture, as illustrated in this figure. So, and here we can see all output results from the MTS device, material testing system, under different needle valve setting and opening and damping levels. From this test, we obtain force velocity and force displacement hysteresis curves. The shape and trend of them actually represent the amount of damping and stiffness that we had in our setup. So the next step for calculating the efficiency was determining the incident wave power. To calculate this, we obtained the wave elevation time series from the first wave gauge. Since it took about approximately 10 seconds for a wave travel from the wave maker to the first wave gauge, we extract the first 10 seconds of signal. Then by applying fast Fourier transform, FFT, we obtain the wave spectrum. So once we had the wave spectrum and determined the group velocity from the dispersion equation, as you can see here, we could then calculate the incident wave energy flux and integrate over the group velocity and wave spectrum, then to calculate the efficiency of the device, or CWR, capture reach ratio. Just need to divide the absorbed power to incoming wave energy flux. The main output from our experiment is here, was the power output of each float shape, which was obtained directly from the load cell measurement. We repeated each test at least 3 times for each float shape and consider the average value as representative output power. So at the end of the day, the comparison was performed based on CWR. The x-axis was normalized using the natural period to allow a fair comparison between different flow shapes. In this graph, as you can see, each data point represents one-time domain analysis result from both numerical and experimental analysis. And you can see how changing the float shape while keeping the same mass and natural frequency can affect the overall efficiency of the device. So in addition to these results, we also evaluate the uncertainty in our experiments. As I mentioned earlier, each experiment was repeated at least 3 times because it's a experimental test with many errors. So using the results from these repeated tests, we calculated the coefficient of variation for each float shapes. These are uncertainty of incident wave, which are unavoidable in our calculation. So finally, we calculated the uncertainty associated with the output power of each float shape using the coefficient of variation, as I explained. Several factors contribute to this uncertainty, one of which was the uncertainty in the incident wave power, which had been estimated earlier. So I've also included a small numerical section in this presentation to provide additional insight into the results. In addition to experimental work, numerical simulation were done to provide a deeper understanding of the hydrodynamic behavior of different float geometries. The numerical model help us to calculate hydrodynamic coefficients like added mass, radiation damping, and wave excitation force, like the equation on top right, as you can see, and perform additional analysis that are difficult to obtain experimentally. And these results complement the experimental measurements and help explain the observed performance difference between all these 3 geometries. So we got then all hydrodynamic coefficients, and then we got post-processing, extract joint force, angular velocity, and absorb power. And finally, we measured or calculated the capture reach ratio, and then we could compare them with our experimental test. So This slide presents the numerical time domain results for three flow geometries under different power takeoff damping values. Each curve correspond to the different damping value, and each data point represent a separate time domain simulation at the given peak wave period. Actually, our objective here was to identify the optimum damping for each flow geometry by determining the damping value that produced the maximum absorbed power at each peak period. So these optimum values were then used in the perform comparison presented in the following slides. So once we obtain the power output for each combination of peak period and damping, we could calculate the CWR, capture reach ratio, or the efficiency of the device to evaluate the efficiency under different wave periods. As you can see, these 3D surface plots shows the relationship between three parameters: damping, CWR, and peak period. So to identify the optimum operating condition, we first calculate the capture reach ratio, CWR, over a range of PTO damping values and peak wave periods. For each peak period, we select the maximum CWR, and the corresponding damping values was defined as the optimum PTO damping for that period. So the 3D surface on the top shows how CWR varies with both peak period and damping, while the plots show on below the optimum CWR that used to compare the performance of the three float geometries. So again, this CW graph represents a fair comparison of the float shapes under both constant damping and optimum damping conditions. As you can see, there are noticeable differences not only between the different float shapes, but it's also between the results we got using the constant damping and those obtained using optimum damping. Thank you very much for your attention. I'm happy to answer any question, and I would like to acknowledge support of Blue Economy CRC again. Thank you so much.
Thank you very much, Reza, for your interesting presentation on your research in wave energy. I'm going to invite, of course, our other speakers, who I also thank for presenting today, back onto the screen as well. So thank you for all making your video available. I also want to invite a co-facilitator for the Q&A session, Dr. Yunil Chu from the University of Queensland. He's been an important research fellow that's been working with the Blue Economy CRC for several years now, nearly the beginning of the CRC, since the beginning, in offshore aquaculture structures as well. So thank you, Yunil, for joining me in hosting this Q&A. Many of you as presenters, you did, of course, excellent presentations, very interesting. And I know that we've had a number of questions in the Q&A that many of you have taken the time to answer for those who are listening. So I appreciate that very, very much. Given that we've got a little bit of time, I thought maybe we could still have some questions that we could discuss here based on your presentations, if you're happy to do so. So, Yunil, I might invite you actually to ask the first question.
Yeah. So you wanna introduce the first question, which you already
No, I
answered?
can do that. Sure.
Yeah.
So I was actually very interested. Xiang Feng, you gave a really interesting overview of what's happening in China at the moment. And from all the projects that you've reviewed, I'm really interested to ask you a couple questions. What do you think has been, what's the single biggest lesson from China's experience in offshore aquaculture that other countries could learn and could adopt or avoid, perhaps, if they're looking at developing or are developing offshore aquaculture?
we are also learning from the practice. Sometimes we are doing it too rapidly because, but because I have some discussions with the industry who installed practically the facilities, we do have some challenges and issues. If I want to summary or give you one suggestions, I would see that to do it is not easy. We need to, at the beginning, make group, make sure that different people can make their words clear. Because now I feel some projects just installed without the perspective opinion from our researchers. I don't think, for example, the fish will fail or to withstand the strong storms. So I think one suggestion I will give or one lesson I will give to you is it's important to have different voice from different communities, environment, policy, industry, manufacturing, and research is important.
Thank you very much. I think that certainly aligns very well with the approach of the Blue Economy CRC in the way in which we've undertaken our research, in particular the sea fisher research, where we've been developing the novel offshore fish pen, which you've seen presented at previous OMAE conferences as well. And of course, you've been part of that symposium as well. Can I ask a follow-up question? Mainly, you spoke about offshore aquaculture developments, but is China considering co-location with offshore renewable energy? And have you seen any examples where they're doing co-location, where they're exploring the integration of the two? And could you speak to that?
Yeah. Actually, we have done some projects about integration with renewable. So I showed in my presentation some already co-located within the offshore wind farm, especially the fixed facilities, which are more safety from owner perspective of wind farm. And then some field facilities also use WEC, with energy convector, to produce energy for their structures performance operation. And then solar energy is also one, I would say, relatively mutual technology used with the offshore aquaculture facility. So till now, we have three types of renewable energy integration. Then another trend is to combine different, well, we call it cost structure integration. So we use one structure, but for both tourism, for both tourism, aquaculture, and energy reduction production. But still now we have few examples, but I know they have some challenges. So they farmed only a little bit fish to see what happened when we use a cost structure.
Thank you very much. Yeah, that's right. I think they're still in prototype development stage, small scale. That's right. Yeah, thank you very much. I think that's really interesting. Please let me know if you would like to ask any questions to the speakers.
I have a question to Ali for the first presenter.
Yes, please.
Ali, I appreciate your effort to simulate this seaweed culture interaction with the fluid and the resin. But I just wondering, your simulation looks like all the seaweed culture is kind of floating. But I don't know, is there any other the kelp species which has a growing downward, which is heavier than water density?
Okay, thank you, Yuni, for your question. That's an interesting one. Actually, so as I had it in my introduction section, my focus is on developing a model that replicates the natural behavior of the giant kelp, which is specifically is like the total density is less than the water, so it's floating as it has the pneumatices and different parts. So the bulk density is lighter than the seawater, so that's why it's growing upward. But we have other species as well, like sugar kelp, that they're growing downward, and yeah, it's like kind of different story with different types of platforms. But yeah, my main focus was on just giant kelp species. So that's why they were growing up with a lower density in comparison to the seawater.
Okay, I think in the future you may study with this heavy density kelp and then see
Yeah,
see some kind of comparison between two different interactions.
sure, for sure. Yeah, yeah. It's a good
Okay,
point. Thank you.
thank you.
So, Ali, one of the things you've been focusing on is, numerically modeling the artificial upwelling to improve the nutrient availability to the seaweeds. But it also requires energy. Have you at all considered how the overall energy cost compares with the gains that you would get in the productivity from growing the kelp? Is there a strategy there? And it might not have been part of your project, but are you aware of some work that's been considered?
Yes, of course. Actually, that's an interesting POV on this because energy, of course, is very expensive, especially in offshore regions. So, as I also mentioned in my the introduction slides, we have different mechanisms for bringing this nutrient-rich water into the surface. So, one of them that is more kind of renewable and sustainable is the wave-driven pump. But what my project specifically was focused on was just using CFD tools in order to track this density-driven plume. So I didn't model the part that is operating in order to bring the water up, but what I was focused on is starting from the outlet of the pump. So what's going to happen if we introduce like the density, the more dense water with a momentum that is produced by the pump, any kind of pump. And so what's going to happen to this dispersion of the plume? Does the kelp canopy gonna behave like a bluff body and doesn't let the dense water to be dispersed, or uh, how they actually interact, like the flexible kelp model and also this pumped density driven flow, and also considering the offshore hydrodynamics like the wave current and even their combination. So this is what was our mostly focused, but yeah, uh, there
Thank you.
should be, yeah, no
Yeah,
worries.
no, that's an excellent response. Thank you, Ali. Very good job. Thank you very much.
Thank you, Irene. Thank you.
Yes, Hongjung, thank you for your presentation. It's a little bit of a look at hydrogen vessels, especially in particular for a specific application around in this case, a service operation vessel to support offshore wind. Mostly operations and maintenance, which I thought was an excellent application for hydrogen. And I've been fortunate to be involved in the work, but many people always ask these sort of questions around, hydrogen as an emerging low carbon marine fuel. What do you think is going to be the biggest technical or operational advantage of using hydrogen with other alternatives, for instance, that we're seeing with vessels such as batteries or methanol or ammonia as other derivatives? What do you think in this aspect, given your expertise?
Yes, thank you. Thank you, Professor, for the question. Yeah, the industry is exploring different alternative fuels like hydrogen, methanol, ammonia, and LNG. Just last week, there's the biggest bio LNG has been bunkered in Rotterdam, port of Rotterdam. There was 11,000 tons of cubic meters of bio LNG. So the maritime industry is looking at a different solution. But for hydrogen, to my experience, that from operational side, I think the advantages are, for example, the first advantage is, of course, the low carbon. It can reach zero emission. And secondly, I think it's in particular for passenger vessels, it's very quiet. If you use prime fuel cell, you can't hear anything. It's not like internal combustion engines. There's no noise at all.
Mm-hmm.
So that's the biggest advantage. And another side I want to say is the safety. a lot of people think hydrogen is very, very dangerous, but actually, we did some CFD simulations, and we also interviewed some experts from the hydrogen industry. Actually, a lot of the experiments have been conducted. For example, liquid hydrogen release or compressed hydrogen release. Actually, and also, Toyota, several years ago, they tested the compressed hydrogen tanks for Mirai, the hydrogen fuel cell cars. Actually, hydrogen is not that dangerous. To some extent, it's safer than other. Maybe it's some people don't agree with this. Because hydrogen, the density is very light. If there's a leakage, it can go upwards very quick. So the dangerous materials actually doesn't exist there. If it's oil or other alternative fuels, there will be a lot of dangerous materials there after leakage, but hydrogen disappears in no time. This is one step. Another says that for all the hydrogen technologies, there's very high standards. For example, currently in the maritime industry, all the classification societies, they have issued their rules or guidelines for using hydrogen on vessels. They proposed a lot of the safety requirements. For example, the hydrogen storage tanks. There's a lot of the safety barriers for that. And also the hydrogen pipelines, they should be piping pipe, double walled. And for the engine room, there's a lot of safety measures as well. For example, more detectors and more, for example, the air change rate is very high and very good ventilation systems there. So I think nowadays the technology and the safety measures can we can use hydrogen safely. So yeah, that's my opinion on hydrogen. But the challenge is there, the cost is very high. So we need to scale up the production and find off-takers of hydrogen to make the industry more healthy and to reduce the cost. Yep.
Thank you very much, Hongzhong. That's a very, very good response and very aligned with what we're finding, of course, in operating the green hydrogen production and research facility in Hobart, Tasmania, and the current trial that we have underway, a bus trial, but very interesting. And there's been a lot of work done on the technology, in particular fuel cell technology and the other derivatives of hydrogen as well. So I see all of them being in the market at some point, supporting the decarbonisation of the maritime industry. So I think excellent work, and we look forward to seeing more of your work on the case offshore production and supply all offshore. So thank you very much for that. I appreciate that. Reza, thank you for talking about your research in wave energy.
Thank you so much.
It's very, very interesting. Your research has been developed, as you said, off the back of the work that we've been doing in with the University of Western Australia and other partners in the Blue Economy CRC, where we've been testing the M4 wave energy converter, which is an attenuator type wave energy converter in the King George Sound in Western Australia. And it's a particular type, obviously, of wave energy converter. There are other types as well, as you know. In terms of your research, especially because you considered the different float geometries and you looked at, of course, the different experimental performance and the PTO, I was really interested in, as wave energy devices move towards commercial deployment, which device parameter do you think offers the greatest opportunity for improving the overall efficiency? Is it going to be the geometry? Is it going to be the PTO design? Or is it going to be the control strategies? Or all of the above?
To be honest, I have to say just the power takeoff system and the control strategy, but I can't ignore my research about the float shape. But yeah, all of them actually, they affect the overall efficiency of the device altogether. So we should work on all parts one by one.
And I mean, I saw the results that you presented today. I generally don't ask this question of PhD students when they're doing their research because they trust their research, right? And I think that what you've got there is correct. But were you surprised in particular of any of the results that they didn't match when you were looking at those different geometries? Your intuition didn't match the experimental performance?
Yeah, as I showed in validation part, some part that was based on the nonlinearity in our model, yeah, we had a not match with our experiment in one of just our results.
Yeah. All right. Fantastic. Is there any questions remaining? I can see that in the Q&A there are no open questions. Is there any question that you may like to ask?
I'm okay.
All right.
Yeah.
Well, we've had 4 very interesting presentations, and I really appreciate every one of our speakers. Ali, who started talking to us about artificial upwelling and kelp dynamics, and then we moved to Hong Jung Fang, who spoke to us about decarbonisation of offshore vessels, in particular an offshore wind support vessel. And then we moved, of course, to Xiang Feng Jiao from South China University of Technology, South China, yes, University of Technology. And I wanted to say thank you very much for joining this as a collaborator of ours overseas. Thank you very much for your presentation as well. We always love to hear about the scale of developments that are happening in China in offshore aquaculture. And of course, Reza as well from the University of Queensland. Thank you as well for giving us some of your knowledge around your experiments and your modelling around wave energy converters. It's been a very interesting session, and I thank you all for presenting today off the back of the OMAE conference and the Blue Economy Symposium, because I love to try and bring the research that we're doing in the CRC not only to the international aspects of conferences, but also to this webinar series, which many other people will have an opportunity to listen to your excellent research. And if I can thank as well my co-facilitator, Dr. Yunor Chu, who actually did much of the work to put this webinar together, but I've taken all of the glory as the facilitator. But I thank you very much, Yunor. I always appreciate everything that you do and your excellent work as well. So on that note, I'm going to thank you all for attending. Thank you all for presenting, and I wish you a good day, a good evening or morning or afternoon where you are, and we'll see you in the next webinar. Thank you very much.
Thank you very much.
Thank you, Irene.
Thank you so much, everyone.
Thank
Thank you
you.
all.
Thank you.